So welcome and thank you for joining us for today's webinar. I'm John Nalaboff. I am filling in for Lorraine Huang today. And so then just a few quick announcements before we get to Renee's talk. So this year our webinar series is emphasizing software and is going to take a deeper dive into some of the features of some of our most popular software packages. And so then a few housekeeping announcements first. So today's webinars, like all webinars, is being recorded and will be available for on-demand viewing through geodynamics.org. During the webinar, only the host and the presenter will have their microphones enabled, so please use the chat window to type in your questions or to communicate with others. During the Q&A session at the end of the talk, if you would like your microphone enabled, please raise your hand. And so today's webinar speaker is Rene Gassmoeller from Colorado State University in Fort Collins. Rene received his PhD from JFZ German Research Center for Geosciences in Potsdam. His research interests include studies of the interactions between plate margins and plumes and modeling of subducted slabs. As a postdoctoral fellow, you may recognize his name on one of the maintainers of the mantle convection code aspect. Today, he is going to talk about one of the features and aspect that he has been a key developer of, and the title of his talk is going to be Intricacies of Particle and Cell Methods in Convection Models with Adaptive Meshes. He's using Aspect's particle implementation. All right, and with that said, I will turn it over to Rene. Thank you.
Thank you very much, John, and thanks everybody for joining in to today's webinar. I will talk in this next hour or so about the lessons that we have learned implementing modern particle and cell method in the mantle convection code aspect. This was work done with many other people at different institutions, and I would like to give a short outline of my talk, which will start with some concepts about particle and cell methods and explaining some basics. Then the challenges that we faced when we implemented the new algorithm. In particular, I will talk about the flexibility of particle and cell methods, the efficiency of the implementation, and how to make modern particle and cell methods scalable to large model sizes. And I will end with some applications that we have done. And I thought it would be interesting to give a very short tutorial on how to use Aspect's particle implementation. So first, let's talk about the particle and cell method. In many domains of computational fluid dynamics, we want to solve a certain set of equations. And one part of the set of equations usually governs the flow of the material we are interested in. These would be, in this case, for example, it's the equation 1 and 2, which is a simplified Stokes equation that we often use in mantle convection simulations. And then there's another set of equations that is usually used to advect some kind of quantity Q. This might be temperature, this might be composition or something else. But in general, it's an advection or advection diffusion equation that in many cases is advection dominated and poses some specific problems. In particular, it is hard to advect sharp gradients, as we, for example, are interested in the Earth. And the concept of particle and cell methods is then to transfer this quantity Q from a continuous domain onto a set of discrete particles represented by the white and black dots in the upper right figure, and then advect these particles instead of the continuous field. This essentially mathematically transforms the advection equation 3 into a set of ordinary differential equations for each particle, namely the equation of motion of each particle. The first reference to this method I found, or is generally known, is actually quite old. It's from the 1950s by Evans and Harlow as a method to solve Navier-Stokes flow in two-dimensional domains. Later on, there were many variations of this method. For example, the marker and cell method, which was used to track the free surface of a fluid, or other methods. For example, in geodynamics, there's a quite well-known paper by Guerra in 2003 describing how to use marker and cell method for lithospheric models. Particle and cell methods themselves have certain advantages and certain disadvantages compared to a field-based approach. Advantages are, for example, that you can attach an arbitrary number of properties to these particles without increasing the computational cost. They will be advected just like with the flow. And you can insert the particles at your particular point of interest. You can essentially control the resolution of these particles. And of course, the properties that you attach to these particles can stay constant over time. So you prevent one of the problems that you have in a field-based method where you diffuse gradients over time. However, they also have disadvantages. They are relatively costly, especially if you have curved or arbitrary domains where you don't know much about the general structure of the domain. You introduce an additional advection error because you have to solve this ordinary differential equation for each particle. And you need to interpolate from the particles back to the mesh to actually use their properties to compute the flow of the next time step. So you add an additional diffusion during this operation. And I added a point here, poorly constrained accuracy. This actually mostly means there is little information about how many particles you need to achieve a certain accuracy for your field. Especially in geodynamics, it's often kind of it's a number that you can tweak and hope that you have the correct accuracy to resolve whatever you want to resolve in your model. Still, the advantages have made particle and cell methods a very popular tool in many different geodynamic domains. Here I've posted 4 quite well-known papers about different aspects of geodynamic modeling. The upper left is a model about the evolution of the whole mantle with a dense layer close to the core mantle boundary. The upper right one is an interaction between a subducted slab and the core mantle boundary. The lower left one is the interaction of a rising mantle plume with a continental rift, so a plume lithosphere interaction model. And the bottom right one is a typical subduction model in 2D. You can see that these models are very different, but they all rely very heavily on the particle implementation of their particular code. And from this, we already see that if we want to implement a new particle implementation in a code that is meant to solve very different problems like aspect, we need to make this method as flexible as possible to make it possible to do all of these kind of models within aspect. So the challenges that we faced when implementing a new particle algorithm in aspect are the following. I mentioned the flexibility for different applications. So that essentially requires that we make no assumptions about the carried properties of the particles. We don't know how many properties they will carry. We don't know how often they will be updated. We don't know how often we want to write that into output files. But still, we need to implement this in an efficient way, and in an efficient way that is independent of the problem domain and independent of the mesh that we are using. So we can make no assumptions about the bounding geometry of our model, for example. This also means we can not create an auxiliary mesh that helps us to locate in which cell a certain particle is at a certain time. This is, for example, a strategy that is used by Sitcom, a quite well-known mantle convection code. Then we want to have these particles implemented in a way that allows to scale the models to very large problem sizes, because as more and more computational power becomes available, also the model sizes tend to grow. This in particular forces us to develop load balancing strategies for the particles in adaptive meshes. Uniform meshes are usually fine because the particle and cell method is very easy to parallelize on these meshes. You usually have the same amount of computational cost for each cell. But if you have adaptive meshes with different numbers of particles per cell, it's very hard to balance this computational load efficiently. And the fourth point is, if we implement all of this, it should be easy to use, it should be tested, and it should be implemented in the available development version of Aspect. I will talk in this presentation mostly about points 1 to 3, and I will leave the point 4 with just the message that we use the same techniques as for the rest of the development of Aspect to make sure that the implementation remains usable. This in particular includes documentation in the source code, documentation in the manual, and a continuous testing of a certain set of models that are tested with every change to the code to make sure that we do not introduce any changes to existing model. Let's start with the flexible implementation. After some testing and some thought about this problem, we came up with an implementation that encapsulates different functionality into a kind of layer structure. There is an internal core part of the algorithms, which we call a particle world, that essentially owns all of the particles, and that is responsible for the internal algorithms, like sorting the particles into cells, like sending particles to other processes in parallel. All of these things that users are usually not, well, they don't need to care about that. It is handled by this internal core layer that you usually will never see. But then there are tasks of this core layer, like the generation of particles or the integrations of particles in time, that depend on the purpose that you want to do with these particles, the goals of your study. Therefore, there are certain interfaces which allow users to select different particle behavior, like different generation strategies for particles. And for each of these interfaces, there are several different implementations, which are usually relatively short source code files that are relatively easy to write and to modify. And all of them exactly do like one particular purpose, like a statistical particle distribution. These are easy to access and easy to change for users. And with this strategy, it's not only possible to write efficient code, but also to make it easy to extend. And we are relatively confident that our implementation allows most of the usual application cases for particles. Let's see how this flexibility looks in practice. For example, the generation of particles is oftentimes something that users want to control because it will allow you to exactly do what you want to do with these particles. These are different examples for how to generate particles in a rectangular domain. There are, for example, statistical distributions of particles on the left-hand side with either uniform or variable particle density. You could imagine generating particles in certain regular patterns, like in the middle column or in the top right. But oftentimes it's also beneficial to just prescribe a certain set of particles, a certain set of locations where you would want to generate particles. And therefore, we also allow to create a data file which prescribes every single particle position, which is the bottom right figure. Another part that is worth thinking about flexibility is the advection of these particles, because that governs the accuracy and the stability of this advection scheme. What you usually want to do in particle schemes is to solve the equation of motion for each particle. But of course, you have to make approximations to solve these equations. And there are several ones, and some of them you usually don't think about. For example, approximations that you usually have to make is that the velocity that you use to advect the particles is only known in a finite element space, or whatever way you discretize your velocity solution in your model. That means if you want, for example, to compare the accuracy of your particle advection scheme to an analytical solution, you should make sure that your analytical solution is represented in the finite element space or discretization of your velocity. Second, the time that you have in this ordinary differential equation is usually only known at discrete time steps. You don't solve the Stokes equation for every, like in a continuous way. You usually solve it at certain discrete time steps. So if your integration scheme for this ordinary differential equation requires the velocity at halfway time, for example, you need to think about how to get this velocity at this halfway point, for example, by interpolating the two surrounding discrete time steps. And then the usual advection error that many people think about is the approximation of the differential operator of this equation. And for this, you can use several different integration schemes, each of them having different accuracies, of course. For our implementation, so far we have implemented a simple explicit forward Euler scheme, the Runge-Kutta 2 and Runge-Kutta 4 scheme. And we have shown that they all scale, like they converge with their correct rates towards analytical solutions to show that the implementation is correct. Last, speaking about flexibility, every tracer has to carry this property Q I talked about. And it usually carries a set of properties. And for the particle, it doesn't matter how many properties that are or what their meaning is. But you need to have some kind of structure in your implementation that can transform the pure like vector of doubles, for example, to a meaningful quantity. And this okay. It seems I lost the connection for a second.
I can hear you now, Rene.
Okay, great. Then I'll continue and I'll Okay, I get an echo from you, John or Lorraine. I will mute my audio for a while just to be able to continue. It seems better now. Okay, so each particle carries a number of properties, and you have to know what these properties mean to actually be able to visualize them in a reasonable way. So in this example, each particle carries the individual components of a deformation tensor. And in this picture, we just see one of these components, but you need to have some property information that tells you that these components of the particle properties are the components of this tensor. And this is also described in these property plugins that I mentioned earlier. So to summarize the flexibility of our implementation, we are confident that the separation into a core part and implementation part of simple plugins is flexible enough for most use cases, and that even if one particular use case is not supported, it is relatively easy to extend the implementation to a particular case. Let's come to the next topic. Talking about efficiency of implementations is not very simple and could fill a whole talk on its own. There are some famous quotes about the optimization of computer programs. Let's start by one by Michael Jackson. The first rule of program optimization, don't do it. The second rule of program optimization, for experts only, don't do it yet. That's not very helpful if you know that you have to do program optimization, but it should make you careful about what you want to optimize. Because usually more computing sins are committed in the name of efficiency without necessarily achieving it than for any other single reason, including blind stupidity. So we should make sure that now that we have a nicely structured and flexible algorithm to not destroy this flexibility by trying to optimize this algorithm for a particular purpose. We need to keep this in mind during the process of optimization. So that's all very nice, but it doesn't tell us what to do to optimize this program. Another quite well-known code in software optimization community is we should forget about small efficiency, say about 97% of the time. Premature optimization is the root of all evil. Yet we should not pass up our opportunities in that critical 3%. So this helps us more trying to optimize our particle algorithms. We should look for these critical 3% and trying to optimize them to a degree that is sufficient. But where to look for them? Like, you could try to guess, but usually bottlenecks occur in surprising places, so don't try to second guess and put in a speed hack until you have proven that's where the bottleneck is. And to do that, we can take a look at the timing output that Aspect nicely provides after each model run. I've posted here a timing output of one particular model I run with the latest release of Aspect. I've removed some lines that are concerned with the Stokes solution and other parts of the algorithm to focus on the particle solution. The numbers that you can focus on are the 50.6 second at the top, which shows the total runtime of the model. And 36 seconds of these 50 seconds are spent in the post-processing part. Currently, particles are categorized as a post-processor in Aspect, so they appear here. So that's a lot. 36 of 50 seconds is spent in the particle advection part of this particular model. And of these 36 seconds, we see that 16 seconds are spent in the advection part, the first line, and 16 seconds are spent in the sort part of the algorithm. So this immediately shows us a lot of code, like the generation and the initialization and initialized properties and output, that we can forget about when we want to optimize this code. We need to focus our efforts on the advection and on the sorting algorithm. Now, how to do that? The advection code is still a lot of code, and we don't know where this time is spent. To further analyze the speed, there is some handy software around, usually open source and easy to use, that can show you in which part of your algorithm you spend how much time. I used the software CallGrind to analyze this, to profile this software, and the software KCacheGrind to visualize this. And this will give you such a nice tree, like in the figure on the right, showing you for each function how much time did you spend in that function, how often did that function call other functions, and where did they spend their time. In this example, the advect particles function on the top needs 7% of the total runtime. It calls 83 times the function local advect particles, which is like advect all particles of one cell, which again called other functions, and this way you can walk your way through the code to find the places where you spend most of your time. Typical problems that you will find when you walk this way through the code is work that is done unnecessarily. For example, that is done twice or 3 times, although you should just do it once. Sometimes functions are called with something that is called pass by value of parameters, which slow down the model if the parameters are complicated or large. Dynamic memory allocation can be very slow if you do it hundreds of thousands of times or millions of times. And oftentimes you have an trade-off between the computation of a certain property that you have to compute several times versus the time it costs to store that property and access it again after a time. All of these are more or less technical things you can improve by doing this profiling. However, sometimes you find an algorithm that you used to perform a certain task, which is simply too slow or which simply doesn't scale well to large numbers of particles. This is called algorithm complexity. And if you find something like this, you will probably need to change your algorithm to reduce the complexity, to make it faster or to make it scale better. During the optimization of our particle implementation, there were in particular 2 algorithm changes that led to a significant speedup. For one, it turns out it is beneficial to store not only the absolute location of each particle, but also to store the reference location. It means the location of the particle in the local coordinate system of each cell. Because this is usually expensive. If the cell, for example, has curved boundaries, it's a relatively expensive inversion of the real coordinates into the coordinate system of the unit cell to compute this reference location. But you need this reference location to advect the particle, to sort it into cells, and for several other things. So it's beneficial to compute this as few times as possible. And we had to take a deep look at the algorithm that sorts particles into cells and improve that one. And I will talk about this in the next slides. But first, let's take a look what happened after lots of work and lots of changes to the code. At the top, you see the same runtime I posted earlier with the latest release of Aspect version 1.4 with DL2 version 8.4.0 and a total runtime of 50.6 seconds. At the bottom, you see the improvement that we've made to the current development version of Aspect 1.5 pre and the latest development version of DL2. The overall runtime of this model has been cut more than in half. And if you take a look at the post-processing line, which comprises all of the particle, the time spent in the particle part, you'll see that the time went down from 36 seconds to 11.6 seconds, more than a factor of 3. Now we can compare the individual parts of the particle algorithm. The advection part went down from 16 seconds to 7 seconds. That's quite impressive, more than a factor of 2. And it was mostly achieved by all of these technical changes I mentioned on the slide earlier. If you take a look at the sort algorithm, which was 16.4 seconds before, it's now down to 1 second. This is like more than a factor of 15. And this is the kind of gain that you can achieve if you find a more efficient algorithm for something. So let's take a look at this algorithm. The purpose of a particle sort algorithm is to answer the question, which cell did a certain particle move to after a time step? Let's, for example, consider this little gray particle, which moved over 1 time step to the blue position across some cell boundaries. And we want to know to which cell did this particle move to. Of course, the simplest thing to do would be to simply search all of the cells of our domain and check if the particle is in that particular cell. That's very easy to implement. You just have to loop over all cells and check for each cell. However, the work that you will have to do will scale with the total number of cells of your local domain. This can be denoted by a complexity of 0.1 O of 1 per particle. So since you usually also double the number of particles if you double the number of cells in your domain, you will have effectively something like a complexity of O of n squared, which is usually unacceptable for large-scale computations. You can improve this algorithm if you first check which is the closest vertex, the closest corner of the cell to the particle, and then only check the particles around that corner. But you would still have to check O of n vertices. So the complexity would not improve of this algorithm. How can we improve that? We know that our adaptive mesh is usually organized in a hierarchy. There is a set of coarse cells, and each coarse cell has children. And these children can have other children. And each set of children is smaller than the parent cell. So you could start by searching for the coarse cell that contains the particle, and then search all of its children and so on until you find a cell that has no children and contains the particle. This way you can reduce the complexity because it will only depend on the number of levels of your hierarchy, and the number of levels usually scales with a logarithmic function as a logarithmic function of the number of overall cells. So this way you have improved the complexity, but you have to do many checks if a particle is in a particular cell, in a particular parent cell, in a particular child cell. And these checks are very expensive, as I mentioned, especially for curved domains. So what can we do about that? We can make use of the knowledge where the particle was in the time step before. Because can you hear me again? Okay, great. So let's start with this slide again. What can we do to make that better? We can make use of the knowledge where this particle was in the time step before. Because under all normal circumstances, the particle can only move to one of the neighbors of the previous cell. And the easiest way to check that is to check all of the neighbors of the old cell, if the particle is in that one. However, the only knowledge that we have immediately available is about all of the neighbors that share a common face with the old cell. And if we would implement this algorithm, we would have a very nice complexity for all particles that crossed phase boundaries. It would be a constant amount of work because the number of cells around a single cell is always the same, independent of the overall number of cells. However, as you might have guessed, I have drawn more or less the worst case scenario in this mesh. And in this case, we would need to fall back to one of the worst algorithms I have described before. Nevertheless, this algorithm is relatively fast, especially for 2D, and it's reasonable for a small number of particles. According to tests, more or less than 50,000 particles per processor. But we can do better than that. We can first check which of the vertices of the old cell is the closest one to the particle, which would be the upper right corner of the old cell. I'm just seeing that I have a question. Is it possible for the particle to move too fast and go to the neighbor cell, to the no neighbor cell? In principle, that is possible, but in practice, it should not happen because the time step of the computation is bounded by a CFL criterion anyway. And what the CFL criterion essentially says is that no information from one cell can move to more than one cell away, which nicely also prevents particle from moving too far. There are some boundary cases where it's possible. Imagine Okay, sorry for that. I guess the message here is don't rely on Wi-Fi to give a talk. Yeah, as I said, in every normal case, the particle will end up in the next cell. In some very, very rare cases, it might happen. So you would need to have a backup algorithm for that case. Okay, so it's better to check for the closest vertex of the old cell, and then only check cells that are around this closest vertex, which are the red ones in this figure. This has a perfect complexity because you always have to check 3 cells in 2D or 7 cells in 3D. However, you need to find those cells. And that is not exactly trivial because if the closest vertex would, for example, be a hanging node, consider, for example, the upper right corner of the small red cell. This is adjacent to the large red cell to the upper right, but it's not one of the vertices of the large red cell to the upper right. So you will have to do some work to find all of the cells that surround one vertex. Still, this approach is worth it. It has optimal complexity and it's pretty fast. However, I told you the most expensive part of this is actually to check if the particle is inside of one cell. And we would like to reduce this number of cell checks as much as possible. How can we do that? The first guess would be to sort the order of cells which we check according to the distance between the particle and the cell center. Obviously, the particle is more likely to be in cells where it is closer to the cell center. However, again, I have drawn the worst case scenario. If you have an adaptively refined cell next to the one where the particle is actually in, the distance to the center of the cell is also smaller. So most likely we will first check the adaptively refined cell and only find the particle in our second try in the next larger neighbor cell. So that's not perfect for adaptive meshes that we want to use for this algorithm. Still, we can do better. Let me zoom in for that one. Since we already know the closest vertex of the old cell, which is the red dot here, we can draw a line from the closest vertex to the actual particle location, from the red dot to the blue dot, and compare the angle between this line and the lines from the closest vertex and the cell centers. And this angle, or the cell that has the closest angle between the vertex center connection and the vertex particle connection, is the one that we should check first. This should make sure that for nearly all cases, the first cell that we check will actually be the one that contains the particle. And as you have seen, this change of algorithm actually is able to reduce the runtime of this sorting part of the particle algorithm by more than a factor of 10. And scales better. So the more particles you have, the better this algorithm will be. So to conclude this second part, optimizing bottlenecks of your code is worth the time, but you should definitely make sure first that it is a bottleneck you're optimizing. And the current implementation is pretty competitive in time to other particle implementations and fast enough compared to the finite element solution that we have to take care about anyway. There's no point in making the particle part way faster than the finite element part. There's a question about which other implementations I am referring to. So far, I have compared the implementation in a rough way. I have to admit it's a rough comparison to the implementation of sitcom and to the implementations of that are described in the paper by Teckley and King 2003, which are implementations in Conman and in the dead time implementation of Stack 3D. I don't have numbers about the actual comparison, but it's within the same order of magnitude of speed. Actually, another question was that I mentioned the method is fast for the number of particles less than 50,000 per process. And what about the number of particles if there are more than 50,000 particles per process? The last algorithm I described works perfectly independent of the number of particles. So let me go back. This one, only checking the face neighbors, works pretty well up to 50,000 particles per process. But these ones, checking the cells around the closest vertex, work very well independent of the number of particles. Okay, let's talk about scalability. After all this effort we have put into the optimization of the algorithm, we are happy that we have reached a scalability that looks pretty well for weak and strong scaling. These plots show the runtime or the wall clock time that is spent in certain parts of the particle algorithm, independence of the model size in the case of the weak scaling. So each process carries the same size of the domain and the same number of particles. And if you increase the number of cores, you also increase the size of your problem. And in the strong scaling case, you have a certain fixed model size and a fixed number of particles, and then distributed to more and more cores, and the perfect speed up that you can get is usually linear. So if you use twice the number of processors, you need half the time. Uniform meshes both seem pretty much perfect with our algorithm. The red line to the bottom is the time that we spend in the MPI transfer of particles between domains. That doesn't scale like perfectly, but on the other hand, it's orders of magnitude faster than all of the other parts of the algorithm, so we don't worry too much about that. For adaptive meshes, the picture is a bit different. The strong scaling is still optimal. If you use double the number of processors, you will get half the runtime. However, the weak scaling is dependent on the way we balance the computational load. I have plotted two lines in this weak scaling plot, the dashed lines and the solid lines. The dashed lines are the runtimes without any adjustment to the load balancing algorithm that was used before. And the solid lines are an optimized load balancing algorithm that I will describe in a few minutes. So we can conclude that the strong scaling is still optimal, but the weak scaling needs some tweaking in this case. Let me explain that a bit more. What happens if we use an adaptive mesh? In this plot, I plotted the total runtime of a certain model, which are the green columns for 3 different models, and separated that into the time spent in the finite element part and the time spent in the particle part, which are the magenta and the blue columns respectively. In the case we use a uniform mesh, the set of 3 columns to the left. Most of the time is spent in the finite element part, a certain time is spent in the particle part. If we then use an adaptive mesh for the same problem, but reducing the degrees of freedom because many cells are coarser than before, the total runtime will decrease. In particular, because the magenta column, the time that we spent in the finite element part, will decrease a lot. However, the time that we spent in the particle part for the same number of particles will increase because now the distribution of particles is not optimally balanced. The algorithm that we use usually tries to balance the number of cells per process, not the number of particles. So many processes will have to wait for the process with the largest number of particles before finishing the time step. And optimally, we would like to achieve the right set of columns, which also reduces the time that we spend for the particle part. Let's take a look at load balancing techniques that we have available to achieve that. Essentially, there are three possible load balancing techniques that come to mind. The first one is what we call balanced repartition. Instead of balancing the number of cells per processor, we can adjust the partition to also balance the number of particles. The nice thing about this load balancing technique is that we don't affect the solution of our model. We just redistribute the cells and the particles onto different processes. However, as you have seen, even the solid line that I have shown before doesn't reach optimal scaling, in particular in the weak scaling, but it's not too bad. You can usually live with that for medium to not too large models. Other things that you can do is, if you know in advance the region of interest of your model, you can distribute the particles to have a higher density in that region than in the other regions. And since your mesh will also be refined in that region, you automatically get a better load balancing. Of course, for that, you need to know the region of interest in advance. A third way is you can restrict the number of particles that are allowed per cell. If you coarsen the cell and you have too many particles in that cell, you can randomly delete particles. And if you refine a cell and suddenly the cell has no particles left or just a few particles left, you could introduce new particles. However, in that case, you would need to interpolate the properties of these new particles from surrounding particles, which for one adds diffusion. And this is essentially like compromising a part of the reason you are using a particle algorithm. So you need to be thinking about if this is possible for your particular problem. Let's see what this balanced repartition method looks like to visualize it. The general idea is to partition the mesh so that an appropriate sum of cells and of number of cells and number of particles is balanced. So essentially, you introduce a weight, for example, W, for particles that determines how important it is to balance the number of particles compared to the number of cells. I've posted different mesh distributions on different domains on the left-hand side, varying this weight from 0, which essentially means particles are not considered at all for the repartition of the mesh, to 1, which means one particle is as important as one cell to balance across different domains. And you can see how this large red domain shrinks with increasing W, and therefore improves the difference between the number of particles, for example, in the red domain and in the dark blue domain. There's another way to visualize this. You can, for example, plot the ratio between the process with the largest number of particles to the average number of particles per process, and the ratio between the process with the largest number of cells to the average number of cells. And you will see that as you increase the weight, you have something like a decrease in imbalance of particles, but an increase in imbalance of cells. And the usual best spot, where you also reduce the runtime the most, is somewhere in between. Now, the experiments that we have done have shown that it's not extremely important to find the best place, the best weight, the optimal weight. Usually it is okay to be somewhere around this best spot where the lines cross. And usually this can lead to reductions in runtime by 30 to 50%, and they are larger the model size and the larger the number of particles. So to conclude the scalability, Our implementation usually shows optimal strong scalability, and the weak scalability in adaptive meshes depends on the model setup and on the load balancing technique that you use and that you are able to use. But this balanced repartition technique achieves a reasonable weak scalability without affecting the solution as the other techniques. So that is a very worthwhile tool to test first before you go to more invasive methods of balancing the load. There's a question about how frequently the domain is being repartitioned. That happens usually in aspect every time you refine or coarsen the mesh, and that is an input parameter. So you could choose to do that every time step, but it's likely expensive. You could choose to do that every second or fifth time step. That is usually fine. And since, by the way, since this imbalance is mostly generated by this mesh coarsening and refinement, it is also okay to only repartition the mesh during this coarsening and refinement. Particles will move around a bit in between, but usually the refinement step introduces this imbalance. Possible applications of our algorithm. Since we now have an implementation of particles and compositional fields in the same code, this is of course interesting to compare the two methods. So this is one very coarse comparison I did a few months ago. And there are currently several studies underway, especially at the UC Davis, about the comparison between the methods. So I'm not going to tell much about that in this talk. There are some nice applications in lithospheric deformation models. Thanks to John for providing this nice figure in the latest CIG newsletter, in which particle properties like the integrated strain can be used to change the viscosity of a certain model. Other applications we have done so far are large-scale metal convection models, in which we use particles to could use them to track the chemistry. In this model, we actually don't do that, but we can track them to we can use them to track the amount, the distance between the position at the beginning of the model and a certain later part of the model. So we can better visualize the flow this way. I think we are running a bit short on time. That is sad because I might have to skip the tutorial that I wanted to do at the end. Let me very quickly go over that so that we have a few more minutes for questions afterwards. The tutorial should show you how to set up a very simple model using particles in aspect. I chose a simple benchmark model by Tackley and King 2003, which has which is a unit box, relatively simple material properties, an initial condition that will lead to a clockwise rotation of the material, and introduces a thick layer of dense material at the bottom. The expected behavior of this model would look approximately like this. This is the 3D version of the benchmark that I have run here with different resolutions, and the top two solutions are, for example, computed by using active particles, while the bottom one is computed by using computational fields. And this benchmark is especially set up to show diffusion in compositional fields. It runs far longer than usual geodynamic models, and it's kind of the worst case scenario for compositional fields in terms of diffusion and entrainment. And you can see how the particles in the top two rows usually preserve the thick, dense layer much better than the compositional field method at the bottom. However, we don't have an analytical solution, so it's hard to tell which is the correct solution of this model set. I will skip this part. If you have used Aspect before, then I don't need to explain how a typical input file looks like. I will skip right to the changes that you will have to make if you want to use particles. What we essentially want to use or want to do is we want to replace the compositional field by a set of particles and compute the composition of each cell as the cell-wise constant average of particle properties. There are more complicated and more accurate ways to compute the cell-wise composition, but I'm not going to talk about this in this talk. These are all of the changes that you would have to do to use particles and use them to track the compositional fields. First of all, since we want to use a cell-wise discontinuous average of compositions, we should make sure that our finite element representation also uses a discontinuous finite element to allow the representation of our particle interpolation. The way to set up this compositional field to be advected by particles is essentially just adding one line, the set compositional field methods equals particles line. And this is exactly also what happens in the code. We will still have one compositional field, but instead of assembling a matrix for this compositional field and solving this for the new solution, we will simply interpolate the solution from the particles in each time step. This makes sure that it's very simple to switch between the two. It's one if statement in the code. And also, all of the existing functionality of the code will continue to work, because for this functionality, it's also just a compositional field. It just happens to be advected on particles. Additionally, you have to add some properties, some lines, some instructions in the parameter file that activate the particles, that set how many particles you want to have, which output format, which integration scheme you would like to use, and you have to give a list of particle properties. In this case, we want to use the property that's called initial composition, which simply takes the initial composition that we have prescribed for the compositional field anyway and maps it to the particles. And well, essentially, that's the result that you will get, except for the input file that I posted earlier as the 2D version of this benchmark, which more or less looks like the rightmost column. This is a bit advanced topic. We can talk about that if it comes up in the questions. But if you have more than one particle property and more than one compositional field, possibly you would want to solve one compositional field by a field method and another one by a particle method. And the parameter file allows you to specify that, but it's a bit complicated to explain. I will skip that for the sake of brevity. And yeah, well, that's more or less it. As summary, we implemented an architecture aspect that can handle particles in arbitrary geometries and with adaptive meshes. You can flexibly select at runtime which generation scheme, advection scheme, load balancing technique, and which properties you would like to assign to these particles. The implementation is scalable, efficient enough for most application cases, and as I said, independent of geometry and mesh. And it scales to, we have tested the scalability to up to 10,000 cores and investigated the efficiency of 3 different load balancing techniques. And we are confident that this technique is now ready to use for actual applications. And with this, I thank you for your attention. And I am happy to answer any questions that might have come up. That is, if there are any questions. Will particle movement cause imbalance? Yes, in adaptive meshes, it can. because if you have a higher particle density in a refined region of the mesh, and the mesh stays constant, but this region of particle moves to a coarser cell, and this cell is on another process, then you will create load imbalance. So even, yeah, actually that's a good question. Even if you only generate an adaptively refined mesh at the beginning of the model run and then never change it afterwards, you will want to do repartitions later on. Thanks for the question. On linear meshes, do you still see an improvement with the angle checking comparison in comparison to simply checking if it's inside two cells? That depends. I suppose you mean by linear meshes that have straight cell boundaries. Yes, I would guess so. The main improvement of the angle checking compared to the distance checking is that it can handle adaptively refined meshes. Okay, you're worried about possible loss in vectorization due to conditionals. Well, actually, in both cases, you will have to sort the order in which you check the surrounding cells. You could, of course, choose to not sort the cells and just use them, but as I said, the check or if a single particle is inside a cell is so expensive for cells with curved geometries that you don't need to worry about this small optimizations. It might be for straight meshes, as you mentioned, but I wouldn't expect it, and I would definitely want to profile this before saying which one is faster. Does your particles also have mass? When you increase the density of particles, is there any constraint? That depends on what you mean by mass. The particles that we use carry some quantity. That might be mass. But as I'm aware, this is something different from the particles, for example, having an extent or something. So the properties that are carried on the particles can be used to compute the solution to the Stokes equation in whatever way you want. They can, for example, influence the density in the Stokes equation. So if that would be the sense of the question, then yes, they can carry some information that influences the density. Is there any property carried by particles like weight? I guess no, if you are referring to the weight of the load balancing technique. I'm trying to guess what you mean by mass or weight. About the density of particles? Maybe there's a misunderstanding. If I talk about density of particles, I mean how many particles in a certain volume of your model domain are there. I'm not talking about how high is the density of one single particle. By weight, you mean weight for summation. I suppose you mean how to transfer the properties on the particles towards the grid nodes. No, there's not. But you could add one. So in the reference implementation that is currently in Aspect's developer version, the only interpolation algorithm from particles to mesh is the cell-wise constant average, which gives every particle the same weight. But I know that currently there are some studies at UC Davis that experiment with other interpolation techniques, and they might be added to the developer version soonish. But of course, you are free to, or every user is free to write an own interpolation algorithm, which is also just one of these plugins that I described in the code structure section. You're welcome.
Okay. Well, if there aren't any further questions, then I guess let's thank Rene either by the message board or silently. Give a nice round of applause. Yeah, and so then, as always, there is more information on this and all events you can find at our website at geodynamics.org, including the recordings of all our past webinars. And then thanks for everyone for participating and for the questions. And again, thank you to Rene. That was a great talk. Cheers.
Thank you, John.